Good evening. This is Mr. Spinsey, your stat sensei, and I'm going to quickly go through a review, as much of it as I possibly can to help prepare you for the multiple choice test tomorrow. I'm going to warn you right now that I'm not going to show you all the things that you need to show for an FRQ because I need to speed through this relatively rapidly, but I am going to show you how to do well on tomorrow's multiple choice test. Well, one thing I want to talk to you about, because I don't think it's really in the death packet, is what happens if they say, hey, what's the likelihood that you have a z greater than 1.5? But they tell you that it's 1.5 standard deviations above. So if it's 1.5 standard deviations above, they've essentially given you a z-score, which means if I were drawing a graph of that, all z-scores have a mean of 0. And so that means, oh, we have 1.5, and the probability of having a greater than 1.5, I can go back and do a norm CDF. The lower would be 1.5, the upper would be infinity, the mean is 0, and the standard deviation is 1. So here I go. I'm going to run through that real quickly. And again, this is for a z-score or standard or having 1.5 standard deviations above the mean. So second bars, norm CDF. Lower bound we said was 1.5. Upper bound 9.99, mean is 0, standard deviation of 1, in which case we find that about 6.68% of the data is above 1.5 standard deviations. On the other hand, what would be the case if they said, hey, what's the probability of having a being less than 1.3 standard deviation? So we want the probability of having less than 1.3. Well, that's the same as saying z-score of less than 1.3. And so if I were drawing my, I'm going to switch pens up. Pen does not work very well. And once again, we're always centered at 0 because it's a z-score. Well, less than 1.3 is like, oh, we're above, and we're looking for this area right here, in which case we'd be doing a norm CDF lower equals negative infinity. The upper would be 1.3. And of course, our mean is 0 and our standard deviation is 1 because we're dealing with z-scores and all z-scores are like that. So second bars, as long as we're working with a normal. So normal CDF, lower bound, negative 9.99. Upper, we said was 1.3. Mean is 0, standard deviation of 1. We should get a value greater than 0.5 because we know we're over halfway. And sure enough, I ended up getting a value of 0.903. All right, I'm going to try to go in an order that I think makes sense. And what I mean by that is I'm going to try to go in the numerical order, although I may mess up. So we're going to start off with problem 21 because I think this is an important problem for tomorrow. So looking at problem 21. It says in the United States, 75% of adults wear glasses or contact lenses. A random sample of 10 adults in the United States will be selected. Hey, this is interesting. Tell me I have a sample of 10. I need to pay attention to that. Which of the following is closest to the probability that fewer than 8 of the selected adults wear glasses or contact lenses? Now, they gave me a percentage, so they gave me a probability, but they didn't tell me this was normal. But I have a fixed sample size. So the fact that I have a fixed sample size, they didn't tell me it's normal. I think I'm working with a binomial. And so what they're saying is with probability that fewer than 8. We're looking for probability that X is less than 8. Be careful. In this case, less than 8. So we could have 0, 1, 2, 3, ... 7, 8, 9, up to 10, but it said fewer than 8. So that means I'm looking for those values. Well, notice I have more than one value circled. All right. Now, if I'm doing an FRQ, I'm going to have to show more work. But because I'm not, I can kind of go through this kind of rapidly. And this is going to be a binomial CDF. Binom CDF. My trials happen to be 10. My probability is 0.75. And we're looking for an X value equal, and I should have put a probability P equals 0.75. And I'm looking for an X value equal to 7. So in this particular case, I should be going second, vars, binomial, CDF, and we know it's a CDF because we have multiple values circled, binomial CDF. Our trials, we said we had 10. Our probability is 0.75, and we want to have an X value fewer than 8, so that means less than 8, so that means 7. And we end up getting 0.4744, and the closest answer to that one was C. All right. And once again, you would need to show more work. This was our FRQ, but on the multiple choice, you do what you need to do to get done. Tomorrow's multiple choice test is 14 questions, so it should go fairly rapidly. Suppose 80% of jurors come to a just decision. In a jury of 6 people, what's the probability that more than half come to a just decision? Well, first off, let's figure out what half is. 6 divided by 2 is 3, so more than half would be 4. All right, so we need the probability that X is greater than or equal to 4, or the probability that X is greater than 3. Either one would have worked. Now we could have had 0, 1, 2, 3, 4, 5, 6, but we want the probability of more than half, so we're looking for this. All right, we're looking for those values. Well, anytime you don't have 0 circled, you should be doing a 1 minus. And by the way, I know this is a binomial because in this case I have a 6. They didn't tell me it was normal. They gave me a fixed number of trials, which is 6. And they gave me a constant probability. So that tells me, okay, we're working with a binomial. And since 0 wasn't circled, I need to do a 1 minus. Well, excuse me, I should say this. I have more than one value. As soon as I have more than one value, that makes it a CDF. And because 0 is not circled, I need to do a 1 minus. 1 minus the binomial CDF trials equals 6. Probability in this case is 0.80, and we always subtract out the highest value we don't want. Well, we want 4, we don't want 3, so our X is 3. Now, once again, this is not the work that you should be showing on. You need to show more work than this on an FRQ test, but for tonight and for getting ready for your multiple choices, this will suffice. So 1 minus second vars, binomials, CDF, trials in this case was 6. Our probability was 0.8, and our X value was 3 because that was the highest value we didn't want. And we end up getting 0.90112. So our answer in this case was D. All right. You're going to have to take just a moment while I figure out what the next problem is I want to do. And the next problem I want to do is number 41. All right. And by the way, I'm doing problems that I think are going to be most beneficial to you tomorrow. So not that these you had others that were questioned about, but these are the ones that I think are extremely important. Oh, all right. Super important problem. And the E1, it messes people up all the time. In a random sample of 50 mathematics majors at a large state university, their mean GPA on a 4-point scale was 3.6. So basically, we're at a university, the max score is a 4 with a standard deviation of 0.25. Which of the following is most likely true about the GPAs among math majors? Well, let's go ahead and draw a picture about this. So the GPA, all right, they're not talking about the mean of everybody's GPA. They're just saying, hey, what's typical GPA? Well, they said they centered at 3.65. So 1, 2, 3 standard deviations above, 1, 2, 3 standard deviations below, and we have a 0.25. So this makes this 3.90. This makes this 4.15, and this is 4.40. Going the other way, we're subtracting. This is going to be 3.4. This is going to be 3.15. And if I did my math correctly, which I probably didn't, this is going to be 2.90. Now, here's the deal. They said the max score is 4.0. Well, that's somewhere here. Well, if I cut that off, it's like, oh, wait a second. That doesn't even look normal. That looks like it more like it's skewed to the left. As a matter of fact, to be normal, we need 3 standard deviations above and 3 standard deviations below, because that's 99.7%. But at the bare minimum, we need at least plus or minus 2 standard deviations. We didn't get there. So how many standard deviations did we get? What we ended up with is Z equals X minus mu over sigma. And our maximum score was a 4.0. Can't get better than perfect. Minus the 3.65 divided by the standard deviation of 0.25. When I do that real quickly, 4 minus 3.65 and divided by 0.25, I end up getting 1.4. So I'm only 1.4 standard deviations above the mean. And I need to really be able to get to 3 standard deviations. But I could have just drawn the picture and seen that it's like, oh, definitely not. But I could calculate my z-score and go, oh, your highest z-score maxes out at 1.4. That's not going to be normal because we need plus or minus 3 standard deviations. Okay. Really, really important question. All right. We're going to look at number 44 next. All right, on number 44, the waiting time for a commuter bus is normally distributed. Oh, that's important. Tells me I'm working with a normal, with a mean of 8 minutes and a standard deviation of 2 minutes. If there are 3,000 riders, which of the following is the shortest time interval associated with 2,000 riders? Well, first off, if we're working with a normal, if we're looking for a shorter span, there's more area in the middle because the curve is taller in the middle. Obviously, this is 2 standard deviations from -1 to -3, but there's not nearly as much there as there is here. 68% is here, and this would be only 16% over here. So consequently, we want to be centered if we want to shorten the distance, shorten this time frame, but maximize the area. Well, here they're being a little bit tricky. They didn't tell us the probability. So they tell us 2,000 out of 3,000. Well, 2,000 out of 3,000 is really 0.666. All right, so about 0.67. That's interesting, because I know plus or minus 1 standard deviation is 68%. That's interesting. So that's not exact, but it's reasonably close, and so it gives us a good starting point. So this is -1. These are my z-scores, 1, 2, 3 up, and -1, -2, -3 down. So between -1 and +1, we have 68%. But our true mean is at 8, and our standard deviation is 2. So if I just keep adding 2, 10, 12, 14, that's 3 standard deviations, or subtracting 2, 6, 8 minus 6, 8 minus 2 is 6, 6 minus 2 is 4, 4 minus 2. And I'm doing that because my standard deviation will happen to be 2. Now, we didn't want 68%. We wanted a little bit less than 68%. So that means my 6 needs to go up a little bit and my 10 needs to go down a little bit, but not a whole lot, because we're only needing to get to 66%, and that's already at 68%. So a little bit larger than 6 would be 6.1. A little bit smaller than 10 is 9.9, so that should be my answer. Now I can check this out by going and doing a norm CDF. So let's go ahead and check this out with a norm CDF. So second vars, norm CDF. My lower bound is 6.1. My upper bound is 9.9. My mean is 8, and my standard deviation is 2. And we're looking for about 2/3. And sure enough, we're at 0.657, so about 0.66. That's pretty close. All right, so that's a pretty good check for that. Okay. All right, so that's number 44. I also want to look at number 47, which is very, very similar to this, I believe. I believe that's what I'm headed to. All right. So number 47, the waiting times for a new roller coaster are normally distributed. So they're telling us they're normal with a mean of 35 and a standard deviation of 10. If there are 150,000 riders the first summer, which of the following is the shortest interval associated with 100,000? Once again, they're telling us this is normal. So if they're telling me this is normal and they want the shortest interval is going to be in the center. And we know our z-score is 0, 1, 2, 3, -1, -2, -3. And they tell us the mean is 35 minutes and the standard deviation is 10. So this would be 35, add 10 is 45, add 10 more is 55, add 10 more is 65. Subtracting 10, this is 25, this is 15, and this is 5. So we want associated with 100 over 150. So 100 over 150, K. Well, that ends up being 0.667. And just like the previous one, this is 68%, which is not the same, but it's pretty close. So I need to be a little bit above 25 and a little bit below 45. Well, the one that's a little bit above 25, 25.3, but then a little bit below 45 is 44.7. So that looks like that's my answer. And if I put that in as a norm CDF, second bars, norm CDF, lower happens to be 25.3, upper 44.7, mean is 35, and the standard deviation they told me was 10. When I do that, 0.667, right on the money. That looks pretty good. All right. So that's another one that's pretty important. It's very much like the one we just did. Next problem that I want to look at is number 50. The average noise level is a bar, is 36 decibels, in a bar is 36 decibels with a standard deviation of 5. Assume a normal distribution. What's the probability of the noise levels between 30 and 40 standard deviation? 30 and 40 decibels. Well, once again, please note that what I'm showing you is acceptable for multiple choice. It's not acceptable for free response. So as a multiple choice, in this case, our mean happens to be 36. And our lower is 30 and our upper is 40. We want this area. Technically, I should be sitting on probability that 30 is less than or equal to X is less than or equal to 40. And I should be setting up the Z and plugging in. And so I'd be going, all right, if this is an FRQ test, the probability that Z is less than or equal to 40 minus 36 over standard deviation of 5 minus the probability that Z, and by the way, I don't have to show this for multiple choice, but I am doing it right now. 30 minus 36 over 5. But what I need to know is, okay, so that's the way I write that up, and I need to calculate my Z if it's a free response. But on a multiple choice, what am I going to do? I'm going to go, oh, they told me it was normal. So it's a normal CDF. My lower happens to be 30. My upper happens to be 40. I have a mean of 36, and I have a standard deviation of 5. So if I go into this thing real quickly, I go second vars, normal, CDF, 30, 40, mean of 35, or mean of 36, excuse me, 36, and a standard deviation of 5. I end up getting 0.673. So my best answer looks like it's D. All right. All right. So moving right along. I thought, I guess I thought incorrectly. 123. I need to check something. I may have skipped a problem. I meant to do 21 and 23, and I don't know if I did that. I did, it looks like. Um, so the next problem we need to look at is problem number 58. The distribution of the number of moths captured per night by a certain moth trap is approximately normal. Oh, hey, there's a keyword. So we know we're working with the normal with a mean of 103. If 28% of the captures fall below 76, which of the following equations can be used to find the standard deviation of the distribution? Ooh, so we're looking for the standard deviation here. That's important. So in this case, let's draw a picture. Always helps. And they tell me, all right, we have a mean of 103. 28%. Okay, that means it's less than halfway. So this is 0.28. And they tell me that that's 76. Well, anytime they tell me I'm working with a normal, I should write down z equals x minus mu over sigma and start plugging in. Well, when I start plugging in, I go, hey, you know what? I have a mean of 103. We know we're looking for the standard deviation. And they tell me that my x value is 76. Calculated that. Unfortunately, I'm still missing standard deviation. I'm still missing z. But if they give me an area, if they give me an app, I can go use my inverse norm. So I'm going to need to do an inverse norm. And it's going to ask for my area. And my area in this case is 0.28. So second bars, inverse norm. Area is 0.28. We're looking for a z-score. So all z-scores have a 0 and 1. So mean equals 0. Standard deviation equals 1. And I end up getting negative 0.5828. It's like, I have a negative z-score. Does that make sense? And the answer is yes, it does make sense because that means your 5 standard deviations are negative 0.5 standard deviations below, or your 0.5828 standard deviations below. All right. So with that said, and make sure we have our mean and our x value in the right place. So that looks like we have D as our answer for that one. That's a pretty important question as well. So it looks like we're moving from 58 all the way up to 71. So a soft drink dispenser can be adjusted to deliver any fixed number of ounces. If the machine is operating with a standard deviation equal to 0.3, what would be the mean? Oh, so we're looking for the mean. That's not good. Settings said that a 12-ounce cup will overflow less than 1% of the time. So if I'm drawing this out, this is 0.01, and this is 12 ounces. We're looking for the mean. Now remember, our calculator is working left to right. If it's working left to right, this value right here is 0.99. That's going to be important. So I start plugging in what I know. So I write z equals x minus mu over sigma. It's like, okay, we know 12. We don't know the mean. We know the standard deviation is 0.3. But I don't have a z-score, all right? I don't have a z-score and I don't have the mean, so what do? Well, they gave me an area, and anytime they can give me an area, I can go back and go, all right, second vars, inverse norm. My area is 0.99. All z-scores have a mean of 0 and a standard deviation of 1. And so then all of a sudden I do that and I end up getting 2.326. So my z-score is 2.3263. Now, unfortunately, I have to solve this by algebra, so be real careful. You might want to check your work twice. All right, so I'm going to multiply by times 0.3 times 0.3. All right, and then I'm going to subtract 12 from it. And I end up getting a negative 11.3. And people, that bothers people because it's a negative 11.3 equals, oh, it equals a negative m. So I can multiply both sides by negative 1, it becomes positive, and we end up with 11.3 ounces. All right, hopefully that helps with that. Again, another really important problem. 72. All right, so I need to look at 72, the next problem. The distribution of lengths of salmon from a certain river is approximately normal with a standard deviation of 3.5. If 10% of the salmon are longer than 30 inches, which is the closest to the mean of the distribution? So this is exactly the same type of problem. So we sit there and we go, all right, we're going to set this up. And we go, all right, 0.10, 10%, upper 10%, and they're longer than 30 inches. And we're looking for the mean. We don't know what it is. And so I always start off going, all right, z equals x minus mu over sigma. Let's plug into that thing and see what we have. When I plug in, we know we don't have that. We have a standard deviation of 3.5. And we have an x value of 30. So I'm missing my mean, but we knew that because they told us to look for that. But I can also go and get my z-score by doing a second VAR's inverse norm. Now, I should be using second VAR's inverse norm of 0.9 because we're doing left to right. But let's just do this the wrong way real quickly. Well, actually, I'm doing it the right way first. Second VAR's inverse norm and 0.9, mean is 0, standard deviation of 1, because it's a z-score, and we end up getting 1.2815. What happens if I would have messed up? All right, second VAR's inverse norm, and I use 0.1. Well, remember, the normal curve is symmetric, so I get negative 1.28. If I've drawn this up, I sit there and go, oh, it can't be negative because I'm above the mean. It has to be positive. All right, so it has to be positive. So 1.28 is supposed to be our answer for our z-score. And so I need to solve it by using algebra, so be careful with that. All right, don't want to lose points being careless. So times 3.5. And then I subtract 30 from it, and I end up getting a negative 25.5. So negative 25.5 equals negative m, multiply both by negative 1, and we're closest to 26. All right. So hopefully that's helpful for that one. 7172. Now we need to look at problem 86. Problem 86, the distribution of the number of siblings for students at a large high school is skewed to the right with a mean of 1.8. All right. So our underlying distribution is 1.8. We got to be careful about this. With a mean of 1.8, but is skewed to the right, and a standard deviation of 0.7. A random sample of 100 students from the high school will be selected, and the mean number of students in the sample will be calculated. Which of the following describes the sampling distribution of the sample mean of sizes of 100? All right, so here's the thing. We want the distribution of the sample mean. So if you're talking about the sample mean, first off, the mean is the mean is the mean. So the mean is going to be 1.8. All right, so the mean equals 1.8. That's no big deal. Or x bar equals 1.8. It doesn't really matter. The standard deviation, because it's the mean, regardless of the sample size, if it's talking about the sample means, it's going to be 1.8 or 0.7 divided by the square root of 100. So that should give me, hold on a second, I'm having trouble. I don't have my glasses on. That's interesting. It looks like there's a major typo here. So here we go. It does have a major typo. I've not ever caught this. So this is a big deal. 0.7 divided by 100 raised to the half power. So I should get 0.07. All right, so I should be getting 0.07. Hope people are listening to this. All right. Now, my sample size of 100 n of 100 is greater than 30. Therefore, it's normal by central limit theorem, or approximately normal. So approximately normal with a standard deviation less than 0.7. Yeah, it's less than 0.7. It should be 0.07. So our actual value should be 0.07, not less than 0.07, but less than 0.7, which is 0.07. Now, please be careful. It's because this is a distribution of the sample mean. If it didn't have the word mean, if it said distribution of the distribution of the sample is going to be skewed right with a mean of 1.8 and a standard deviation of 0.7. All right. So if it's skewed right, mean of 1.8, if this had sample. On the other hand, if it said a distribution of the X bar, well, X bar is just another way of saying sample mean. So in which case, all right, if it said X bar, we would have said mu is 1.8, standard deviation is 0.07, normal by central limit theorem, or approximately normal by central limit theorem. If they said instead of the distribution of the mean, sample mean or distribution of X bar, they said distribution of the averages. Well, the mean is the average. So the distribution of the average will have a mean of 1.8, a standard deviation of 0.07, and it's normal because, or approximately normal because our sample size is greater than or equal to 30. So please pay careful attention, because if it had just said the word sample and didn't include mean, average, or X bar, then it would have been 1.8, 0.7, and skewed to the right. But because it includes mean or X bar or average, it's going to be this. All right. Now, what happens if our sample size is less than 100? Less than 30. Well, if our sample size right here had been, let's say, 25. All right. Well, if their sample size would be 25, the mean would still be the mean. The standard deviation would be 0.7 divided by the square root of 25. But the shape is not normal. All right. We don't know what the shape is. It wouldn't be normal yet because our sample size wasn't large enough. But in this case, we had 100. It's plenty large. It's normal by central limit. All right. And problem number 95, and that'll be the last one for this video. A new soft drink product has an average of number of 77 calories per bottle with a standard deviation of 4.5. In a random sample of 40 bottles, we have a sample size. That's important. We have N. And by the way, what is the probability that the mean number of calories is between 75 and 80? Well, notice they did not tell me that it was normal, but my sample size is greater than 30 or 30 or more. Because my sample size is 30 or more, the distribution of the means is normal by central limit theorem. So I need to check, are they asking about the means? And sure enough, they said, what's the probability that the mean, not an individual bottle, because we can't do that because they didn't tell us the shape, but they did tell us that we're dealing with the means. And when they told us that, and they have a sample size of 40 or more, or 30 or more, then it's normal by central limit theorem. So we're looking for, and by the way, if we draw a picture, 77 is our mean, that's 4 centered. 75 is our lower X bar, 80 is our upper X bar. We want the probability that 75 is less than X is less than 80. So I'm not going to show all my work because it's a multiple choice test, but normal, well, CDF, of course, and our lower bound happens to be 75. Our upper bound is 80. Our mean is 77, but we have to be really careful about our standard deviation because it's not our standard deviation, it's the standard deviation of X bar. And our standard deviation of X bar happens to be 4.5 divided by the square root of our sample size. Because remember, X bar equals the population divided by the square root of n. Well, our population had a 4.5 and our sample size is 40. So that's our work. All right. So let's go ahead and run this thing. And there's a couple ways to do this. If it's an FRQ test, I might do it using stat test Z test if I can get it. I still have to write norm CDF. I have to include that. So second vars, normal CDF, lower bound 75, upper bound 80, mean 77, standard deviation 4.5 divided by the square root of 40. All right. And I find 0.9975. So about 99.75% of those bottles lie within that interval. All right. One other thing I should note is remember, if you don't know if it's normal, then you can't use the normal. All right. You should also know that the 25th percentile, if I give you the 25th percentile, you should be able to use second var's inverse norm. If I give you the third quartile or the second quartile, if I give you the second or third quartile, you should know second quartile is 25%. I could do an inverse norm. If I give you third quartile, 70, I can do an inverse norm of 75%. All right. Well, I appreciate you watching. I hope you do really well tomorrow. And this is your Stats Sensei. I hope to see you on the next one. And I'm stopping the recording.